Christmas shopping done? Those of you who celebrate Christmas? Everybody should celebrate Christmas, even if you don't celebrate it in the typical ways, right? Everybody should celebrate the birth of Christ, is my point. We should all be celebrating and joyful and thankful in the fact that the God of the universe decided to become like one of us, so that we could become more like Him. Right? As has been said by others, that God is not, or Jesus was not just God in a man suit, right? Like a man in a gorilla suit is not really a gorilla. You might get in the suit and pretend to be one. That's not what Jesus did. I don't think He was laying in the manger, having great and amazing thoughts, saying, "Well, I just got to lay here for a few more months, and then, I just got to do this for 33 years, and then I can get out of this." I think He was thinking about what other babies think about, whatever that is. So, celebrate Christmas. Be joyful. Speaking of which, let's read Psalm 98. Psalm 98. What's that have to do with Christmas? Actually, I think it has quite a bit to do with Christmas. Of course, the whole Bible has to do with Christmas. No, that's not what I mean. You're right about that, but that's not what I mean. There's several passages in here that I think can apply to things that we hear about at Christmas time. Psalm 98, I'm just going to read the first couple verses. Sing to the Lord a new song, for He has done marvelous things. Isn't that what the angels did when they visited the shepherd? They were letting them know the Lord has done marvelous things. His right hand and His holy arm have worked salvation for Him. Isn't that what some of the people were saying when they were prophesying? Like Mary when she was talking to Elizabeth and stuff. His right hand and His holy arm have worked salvation for Him. The Lord has made His salvation known and revealed His righteousness to the nations. Christ is our righteousness, and He is being revealed and has been revealed to the nations. Amen. Let's pray. Father in heaven, thank You for revealing Yourself to us. Love is revelation. When one loves another, they reveal themselves to the other, and You have done that. You have revealed Yourself to us because You love us. Thank You for doing that. Thank You for taking on human flesh so that we could take on the divine nature. May we please You in the way that we accept this gift and the way and what we do with it. In other words, may we live faithfully for You, strive to be more like You, be joyful in You, and thank You. We pray that You bless our class time now in the name of Your Son, Jesus. Amen. I see 10 participants. Wow, that's great. Everybody's here, and all on webcam too. But only 2 scores, so let's have them. You got some scores for me? Boom, here they come. Thank you, Olivia. Thank you, Elijah, and JT, and Annabelle, and Aaron, and Salah, and Marin, and Noah, and Calaboose. Okay. Somebody sent. Yep. The answer, Colin, is yes. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Waiting on 2 more scores. Unless somebody's holding out on me. I think somebody's holding out on me. Why do you say this? Why do you say such things? If you go to the top of the chat box, you should be able to count them off. Let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Aha. Thank you, Annabelle. That's okay. If you did an extra problem, good. You'll just be a tad bit smarter than everybody else today. So we're gonna ask now, from now on, every question I ask today, I'm gonna ask Selah, because she did one more problem than everybody else. So I'm just gonna ask her to answer all the questions. She'd be like, I'll never do homework problems again. Okay. Alright, there is an exploration today, and I'm not sure I'm going to mess with it, because it's hard for me to do on the screen, kind of, and seems like we would have done it already by now, but maybe not. I guess we're talking about the Pythagorean theorem and the distance formula. Now, you all should have seen the Pythagorean theorem before. Yes? You all are familiar with it? You know it pretty well? Kinda, sorta? You got it? You know what it is? You know what it does? You know what it's for? Or something? Aaron, why do you say in the distance formula? I missed the timing here. Are you saying you already know what that means too? Or you've already seen it? Or you're just telling... You have already seen it? Everybody else seen it before? The distance formula? Maybe we should start with this kind of question. Anybody not seen the distance formula? Well, maybe I should just not teach it and just give you all 30 homework problems instead. Well, let's do a little review. So hey, look there, looky there. Isn't that nice? We'll skip the exploration, I think, but you know, Pythagorean theorem only applies really to right triangles, triangles with a 90-degree angle, right? So you know that, and you know that this is the proof that the scarecrow did indeed have a brain, right? Because as soon as he got a brain, he says something like, the length of the hypotenuse is equal to the square root of the sum of the squares of the two sides. Something like that. And so, in other words, if you take the length of this leg and the length of this leg, by the way, the two sides of a right triangle that share the 90-degree angle are called legs, and then the and then the hypotenuse is the third side. The hypotenuse is always the longest side on a right triangle. Okay. So if you take the length of the one leg and square it, and then the length of the other leg and square it, and then add those together, that'll be equal to the length of the hypotenuse squared. And the exploration, I said I wasn't going to do it. Let me see if I can just rough it a little bit. I don't want to spend much time on it, but for sure. But the purpose of the exploration was that, let's say this side A had a length of 3 or something. So we split it up into 3 rows and 3 columns. So we have, what do you know? If it has a side length of 3, when you square it, you get 9, right? And look there, I just drew 9 squares, thus the term squared. And if let's say, this is going to be pathetic, but let's say this over here was, yeah, this is really pathetic. But let's say this side over here had a length of 4. No, that's just terrible. That's not working. Mr. Ralph, you're just wasting our time. I know it. Let's start all over. I don't know. That's not going to work either, is it? The point is, so if this side had it, oh, stop it, will you? That's not helping. There we go. There we go. Okay. If we took and put 9 squares over here and 16 over here of the same size squares, even though mine are really sloppy and so they're not really the same size, but and then we could take, if you took these 16 squares right here on the bottom, if we took these 16 squares and moved them and laid them over here, something like that there, again, really sloppy, but if we put the 16 squares over here, they'd look something like that, right? Wouldn't cover. But then, if you took these 9 squares, you could fit 4 of them here down on the end, and then how many would you have left over? If I use up 4, if I use 4 out of 9, I'll have 5 left over. Well, what do you know? There's 1, 2, 3, 4, 5 in that direction, which means I could put another row of squares up here. And so how many total squares would I have? I would have 25 squares up there, right? And it turns out, so if you measure the length of this thing down here, it's 5. So if one leg has a length of 3 and the other leg has a length of 4 and the hypotenuse has a length of 5, it turns out that 3 squared plus 4 squared, that's 9 plus 16, equals 25. And sure enough, 5 squared equals 25. So he's just wanting you to get a pictorial idea of why this works. It turns out that if you take the one leg and create a bunch of squares and take the other leg and square it, make some squares, that those same number of squares added up will equal the number of squares that you would have up here. So 3 squared plus 4 squared equals 5 squared. This is Pythagorean. This is an illustration of Pythagorean's theorem. Okay. Well, we can use this to find something missing on a right triangle. So if you have a right triangle and you are told that that the hypotenuse has a length of 13 and one of the legs has a length of 5, find the length of the other leg. You could use Pythagorean's theorem to do that, right? You would have to move some things around, but you could do it. So again, let's call the unknown length x, and so 5 squared plus x squared equals 13 squared. That's Pythagorean's theorem. The sum of the two legs squared equals the hypotenuse squared. So this is 25 plus x squared equals 169. Subtract 25 from both sides, and you have 169 minus 25, which is 144. Take the square root of both sides and solve for x. And you just x is equal to 12. So the length, say you can do that kind of thing, right? I'm going quickly because most of you say that you're familiar with this stuff. So you could do this. By the way, let me just read the Pythagorean theorem. Of course, you know, if a triangle is a right triangle, the sum of the squares of the lengths of the legs equals square of the length of the hypotenuse. So if the legs are a and b and the hypotenuse is c, then a squared plus b squared equals c squared. Okay, but then there's the converse of Pythagorean's theorem, and this is kind of neat. And of course, converse of theorems sound a lot like the theorems. They just take the first part and put it at the end, and then they take the end and put it at the beginning. So the converse says, if the sum of the squares of the lengths of the two shorter sides of a triangle equals the square of the length of the longest side, then the triangle is a right triangle. So the point of this is, suppose you know you have a triangle, and suppose you know the lengths of the sides, but you're not sure if it's a right triangle. Suppose I gave you something like this. What if I gave you, say something like this? I have a triangle that has a length of 15, and one of the sides has a length of 15. One of the other sides has a length of 39, and one of the other sides has a length of 36, we'll say. Is that a right triangle? Is that a right triangle? Well, again, you must remember that the longest side is always the hypotenuse. So that means the side with a length of 39 is the hypotenuse. If this is a right triangle. I don't know. It might not be. Actually, I do know, but I'm pretending, right? If this is a right triangle, then the side with the length of 39 is going to be the hypotenuse. So that means that the 15 and the 36 would be the legs. So we can test this. Does 15 squared added to 36 squared equal 39 squared? Don't know, so we'll put a question mark here. Let's test it out and then break out the calculator, because I can't do that quickly in my head. I could do it on paper, I suppose. 15 squared is 225. My calculator is running out of juice. 36 squared is 1296. 39 squared is 1521. I'm still going to put a question mark there because I don't know if 1296 plus 225 equals 1521. So I add them up. 5 plus 6 is 11, carry 1. 9 plus 2 is 11, plus 1 is 12, carry 1. 2 plus 2 plus 1 is 5, and then 1. What do you know? 1521 does equal 1521. Check. So this is a right triangle, because when I plug the side lengths into Pythagorean's theorem, I got a true statement. Now let's take another one. Say something like this. What if I had a triangle with a side length of 6, the other side had a length of 11, and the other side had a length of 14? Is that a right triangle? Well, again, The longest side would be the hypotenuse if this is a right triangle. So so the 14 side, the side with a length of 14 would be the hypotenuse. So 6 and 11 are the legs. So 6 squared plus 11 squared equals 14 squared. I don't know if this is true, so I put a question mark. 36 plus, what's 11 squared? 121? Huh? Is it? And then 14 squared is 196. Okay, so 121 plus 136 is 157. 157 equals 196. No, it doesn't. So this is false. So apparently, since Pythagorean's theorem didn't work on those three numbers, then that triangle is not a right triangle. Now, there is probably a triangle in the world that truly does exist that does actually have those side lengths, right? It is a triangle. It is a valid triangle. It's just not a valid right. It's just not a right triangle. It doesn't have a 90-degree angle in it. I'm not sure what this thing would look like, but it would, you know, maybe look, I don't know, look something like, I say one side length is 6, and the other side's almost double that, and then the other side's even longer. So maybe I should draw it like this. So, you know, it might look close to a right triangle, but actually I could figure out what the exact angle is, but that's a little longer than 90 degrees, so it's not a right triangle. I don't know if that even accurately represents it, but the point is, so you can use the converse of Pythagoras theorem. So the point is, what was the one we had earlier? We had 36, I think it was 36, 15, and 39. That one turned out to all work out nice. So we didn't know if it was a right triangle, but then it worked when we plugged it into Pythagorean's theorem, so now we know it's a right triangle. And that's what the converse of Pythagorean's theorem is telling us. Given side lengths, if the one side length squared plus the other side length squared equals the third side length squared, then it's a right triangle. Okay? So that's the converse. So we talked about that a little bit. So I think one of the last things to mention was the distance formula. While several of you said you'd seen it before, I didn't get 10 answers to that effect. So let me bring something up here. Okay. So hopefully you can see a coordinate plane there, but you can see, right? If I let's see, if I have a point, say right here, and some other point over here, and I want to find the distance between these 2 points. Well, let me get the coordinates here. First of all, 1, 2, 3, 4, 5, 6, 7. So x is -7, y is 5. That's the coordinates for that point. This point out here is 1, 2, 3, 4, 5, 6. X is +6, y is -1. Okay, so those are the coordinates of those 2 points. I want to know what the distance is between them. I want to know what this distance is right here. The distance of that little red line. Okay? Actually, it's probably made a thick red line. But anyway, if you know, it doesn't take a lot of observation, I don't think, to realize, hey, wait, I could turn this into a right triangle by dropping down a vertical line so that the bottom of that vertical line matches the y coordinate of that other point, right? See, this point and that point have the same y values. And then this point up here and this point here have the same x values. So let me just go ahead and finish drawing this in. I could turn this into a right triangle, right? And so this is 90-degree angle here, and this point over here, the distance from here, from here to the other point, that vertical distance is just however many unit squares we have there. 1, 2, 3, 4, 5, 6. So that distance, that vertical distance is just 6. And the horizontal distance from here to here is just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13. So that's 13. So I could plug those values into Pythagoras Theorem to find the length of that line there, which is the distance between the 2 points, right? 6 squared plus 13 squared equals c squared, the hypotenuse, c. And what is that? 36 plus 169, I think. C squared, and what is that? I don't know. Why do you ask me such hard questions? 205 maybe? So c squared equals 205. Take the square root of both sides, and I get c is approximately equal to whatever. What is that? 25 is 15, so 14 something? 14 point something? 14 point something, 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 something. So that's the distance between the points. 14.317. Thank you, Aaron. So you can see, oh, okay, so we can find the distance. Well, what would be nice is to not have to do all this geometry every time. I don't always have to, if you give me, I don't want to have to draw this on the coordinate plane and then count all the little squares, and then plug in Pythagoras Theorem. What would have been nice is if somebody would have just told me what the coordinates of the points were. So at this point right here, before I've drawn anything else and counted things, actually at this point right here, stop sharing and go back to our other blank screen here. At this point right here, stop it. Can I get some cooperation, please? Thank you. See, I don't even need the coordinate. Coordinate plane. If you would have just told me that the points of the coordinates of the points are -7 and 5, and 6 and -1. So remember, the one had coordinates of -7, 5, and the other point had coordinates +6 and -1. Then I could plug those into the distance formula. But the point was to show you that the distance formula, which means I actually need to go back here. To show you that the distance formula is actually just a special application of Pythagorean theorem, right? Let me generalize the coordinates of this point over here. Let's call this point x1, y1. And let's call this point over here x2, y2. So the vertical distance here is just the difference between y1 and y2, right? And this horizontal distance here, in other words, the length of the leg here, is just the difference between x1 and x2. So x2 minus x1, x2 minus x1 gives us the length of that leg. y2 minus y1 gives us the length of that leg. So if I take x2 minus x1, square it, right, the length of one leg squared, plus y2 minus y1 and square it, that's the length of the other leg squared, right? Then that will give me, let's call the hypotenuse d for distance. That will give me the hypotenuse squared, right? x2 minus x1 is the length of the one leg. We square it. y2 minus y1 is the length of the other leg. We square it. We add those together, and that's equal to the hypotenuse squared, d squared. Well, I don't want d squared. I want d. I don't want the distance squared. I want to know what the distance is, not what the square of the distance. So if I take the square root of both sides, then I can just get d. So d is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. That's the distance formula. Now again, you've seen this before. You've seen Pythagorean theorem before, but maybe you don't always fully remember all the details of the distance formula. So hopefully you at least remember Pythagorean theorem. So if somebody asks you on a test or homework to do something regarding the distance formula, even if you forget, you should be able to arrive at it by just remembering, I know it has something to do with Pythagorean theorem. And so you should be able to figure it out on your own if you happen to forget it. So that's the value of showing all of this, is that you can see, oh yeah, well, I know it has something to do with Pythagorean theorem. I think I can figure it out. And sure enough, there you go. So the distance formula is right there. D equals the square root of x2 minus x1 squared plus y2 minus squared. So where x2 and x2 and y2 are the coordinates of one, the coordinates of the other point. So back to the other screen, I have 2 points here. Let's just call one of these points x1, y1, call the other point x2, y2, and by the way, it doesn't matter which. I could call this first one x2, y2 if I want. Let's call it x2, y2, and we'll call the first one x1, y1. It doesn't matter which. Why doesn't it matter? Because once we're done subtracting, then we're going to square it. So it doesn't matter if what's inside here is negative or positive after I'm done subtracting. It doesn't matter because we're going to square it. And every time you square it, if what was inside there was negative, when you square it, it's going to become positive. If what was inside there was positive, when you square it, it's still going to be positive. So that's why it doesn't matter which one you pick as x1, y1 or x2, y2. It does matter that you don't mix it all up. Don't say x1, y2. Don't do that. That gooses everything up. That you'll get the wrong answer. Don't say x2, y1. That matters. You can't do that. But if you want to call this one x1, y1 and that one x2, y2, or if you want to call this one x2, y2 and that one x1, y1, that one's okay. That's okay. So let's plug these into the distance formula. The distance formula is x2 minus x1 squared plus y2 minus y1 squared. So we just plug those values in. Okay, so we're told that x2 in this case is negative 7 and x1 is positive 6. Y2 is 5 and y1 is negative 1. So we're subtracting the negative 1. So we have negative 13 squared, and 5 plus 1 is 6, and 6 squared. So we have positive 169 plus 36. We've done this already, right? So this is what, square root of 205, which we were told was approximately 14.317. So you see, I didn't even need the graph then. Just by being given the coordinates of these 2 points, I was able to use the distance formula, which is really just a special application of Pythagorean theorem, and I can find the distance between those 2 points. So if you give me the coordinates of any 2 points in the universe, I can find them just plugging into this formula, which is solving algebraically versus solving geometrically. This is algebra class, not geometry class. They are integrated, however. But we want to figure out how to solve the world's problems using algebra. That's what algebra class is all about. And so we can solve without creating a graph. So that's kind of cool. All right. Any questions on that? Questions? Okay. Your mission, should you choose to accept it, and you should choose to accept it, is to do, let's do problem G and H, letters G and H. What's this called? Lesson 41 or something? I guess it is. So do G and H, and then these others that I'm about to give you. We have lessons coming up on trigonometry in this class for sure. Yes. We do have those coming up, unless you go to meet with the Lord before we get to that point. So if it scares you that bad, you can ask the Lord to do you a favor. But I'd say, no, just stay here and suffer with the rest of us. Okay. Yes, we do have trigonometry coming up. We will be doing a bit of it. I don't remember when, but we do get into it. What letters did I say? G and H? Didn't I say G and H? Okay. And then 1, 2, 4, 5, and 9. Twelve, 13, 14, 15. Where are we? I keep losing myself. 18, 19, 20. 24, 26, 27. So I think it's total 17 problems. 1, 2, 4, 5, 9. And 12, 13, 14, 15. 18, 19, 20. 24, 26, 27. 3, 6, 10, 15, 16, 17. Yeah, 17 problems. Trigonometry is really nice, actually. But yeah, the early parts of it anyway are pretty nice and pretty fun. We will get into some stuff that won't be near as fun later in the year. Well, it won't be near as fun for some of us. Others of us might love it, so I don't want to sway your opinion on it. Yeah. Well, we'll work on that this year. Coming up with some mnemonics for remembering which is which. But, as Christ said in Matthew 6, take no anxious thought for the morrow, whether you will have to figure out sine, cosine, or tangent. Something like that. He said something to that effect. What will we eat, drink, or what will we wear? Don't worry about these things. Don't worry about sine, cosine, tangent. For today is evil enough. Sufficient unto the day is the evil thereof. King James says. In other words, we'll cross that bridge when we get there. Or as an old country song said, we'll burn that bridge when we get there. Right? Sokotoa. Yeah, wasn't she the one with Lewis and Clark? No? Who's that? Was that Sacagawea? Sacagawea or something like that? Everybody do okay with problem H? There's an example problem just like that one in the lesson. So if you're still on that one or still struggling with that problem H, there's an example much like it in the lesson. Well, he tells you right there, example 4. So that was like example 4. If you have any questions or want to see another problem or two worked on the screen, let me know. Otherwise, you're welcome to sign out. You're welcome. You're welcome. Yep, see ya. See ya.